Okay, I would like to thank all the organizers, especially Logan Suvrat for inviting me here. So this is some work I've been doing. It's ongoing work with my collaborator Miguel Campiglia, who is in Uruguay. And sort of this is a primary motivation of this work comes from a lot of recent work which has been happening in a relationship between soft theorems in gauge theories in gravity and asymptotic symmetries. Okay, so this I mean I will tell you shortly what these asymptotic symmetries are, but basically they are a class of infinite dimensional symmetries which constrain the scattering amplitudes of gauge theories and gravities. And it turns out that so this work primarily was started by Strominger and his collaborators. Sorry if my handwriting is, I mean it won't improve too much, but if it's too small, please do let me know it. Okay. And so the idea is that given any soft theorem in gauge theory of gravity, with actually a given soft theorem is really infinitely many soft theorems because your soft particle really can be in any direction in the sky. So given any sort of soft theorem, you have infinite dimensional symmetries in the theory. And so as you get more and more soft theorems in any given theory, you get more and more infinite dimensional asymptotic symmetries in the theory. And it turns out that now one has sort of an infinite hierarchy of soft theorems in say QED and gravity. And what we would like to understand is how do you classify all possible asymptotic symmetries, sort of an infinite dimensional asymptotic symmetry and infinite hierarchy of them for all these soft theorems. So that's a goal of the work. So what I'm going to, just for simplicity, I'm going to work with massless scalar QED and looking at tree level amplitudes. Scattering amplitudes. So here, this sort of masslessness is not really a restriction. I'm only using it for simplicity because otherwise the formula became very complicated. And instead of scalar QD, whatever I say, most of it would go through even for gravity, except this is a very crucial assumption. Everything I say is really only holds for tree level scattering amplitudes. So let me first start by this is a broad outline of my talk. I'm going to first review what are soft theorems in QED. And then I'm going to recall really the sort of work of Strominger and many other people following their group, which is to relate a certain like two of these soft theorems, a relation of them with a class of asymptotic symmetries. And here we will already see that certain questions arise, sort of whose answer forces us to go beyond what has been done so far. And then finally, I will talk about the work that we are doing, which is to sort of generalize this to all possible soft theorems. So all soft theorems. Asymptotic symmetries. So that's a very sort of a rough outline of my talk. So let me start by telling you what the soft theorems are. So as I told before, I'm going to work with tree level scattering amplitudes. So let's take some scattering amplitude with say n scalar particles, charge particles. I'm going to take all of them just for simplicity to be outgoing, but it doesn't really matter. And suppose we look at insertion of one photon in this theory. So omega is the energy of the photon and q hat is sort of the direction of the photon. Then it turns out that in the limit that omega becomes small, this amplitude factorizes and it can be written as, I will explain the notations as I go. Where by Mn, I just mean the scattering amplitude without the photon. So this is the notation I will use for Mn, where this S0QI is what is known as a Weinberg soft factor. So this theorem was known long time back, I think in 65 or something. And S0QPI is nothing but if polarization of the photon is epsilon, then so this is a sort of this is what is known as Weinberg soft theorem. And this is really a universal theorem in the sense that It is, although I am only working at scalar QED, you could add any interactions in the theory, and as, this leading order factorization will not change. In fact, it is also IR protected. So even if you look at inclusive cross sections or any way you do IR finite scattering amplitudes, this particular factorization theorem will still hold. Sorry, thank you. Yes, I'll put QI here. Thanks. But it turns out that these factorizations don't stop here. In fact, this order omega to the 0 term was also for tree-level amplitudes, were also factorized by a physicist called Low a long time back. And this is given by, these terms are given by sort of later soft factors, which I will just explain. So there's again a factorization, and this S1 in contrast to S0 is in fact actually a differential operator. So S0, S1. Now this theorem in some sense is very powerful because it is a factorization theorem. It's not something you would naively expect if you just look at Feynman diagrams. But it is not infrared protected. So for tree-level amplitude, it's okay. But it will have infrared divergent corrections if you take loops into account. It is also not universal in the sense that if you add irrelevant interactions which change the 3-point functions of the theory involving photon, then this term will change, although the factorization itself will hold. So it is sort of quasi-universal, not as universal as the Weinberg's of photon theorem. Nonetheless, it exists, at least in tree-level amplitude, it's there. But it turns out that recently what people have discovered is that these theorems don't stop here. And in fact, even this order omega terms show some sort of a factorization behavior. And these are, so these order omega terms, one can write them as follows. Let me write it like, where these SKs are sort of similar to these operators, and they are given by it is very similar structure to the one before. Q dot, sorry. So there are additional powers of Q, as you can see here, which get multiplied with a differential operator. So these are higher order differential operators, which sort of operate on this scattering amplitude. But these are not factorization theorem, because there are these remainder terms which are totally theory independent, and they don't factorize into some endpoint amplitude times something. So, but the structural difference between these remainder terms and this one is that these are all differential operators, but these are just ordinary scattering amplitudes. So anyway, so these are some sort of not really factorization theorem, but some constraints on the tree-level scattering amplitudes. And what Strominger and his collaborators and many other after them have shown is that both these theorems are really manifestations of asymptotic symmetries in the theory. And what we would like to understand is that whether even all the other theorems are also manifestation of some class of symmetries in the theory. So first what I would like to do is to sort of revisit the relationship of these two theorems with the asymptotic symmetries, and then go from there. Is it visible? Okay, so in order to sort of write these soft theorems as Ward identities for some asymptotic symmetries, I have to tell you something about the space-time structure. So of course we are working in Minkowski space-time, and it turns out that, so we want to understand what are asymptotic symmetries, what are symmetries at sort of infinity. So to understand that, we should know what is infinity first. So the idea is first to understand the notion of null infinity of Minkowski space-time, because this is where the symmetries sort of operate. And here the idea is, I think Shamik already talked about this, I will be very brief. So the idea is that suppose you work in retarded coordinates. Then in these retarded coordinates, if you keep your u and the direction fixed, and you take large R limit, then you hit what is known as future null infinity, which is really topologically a cylinder, where the U direction is going like this, and you have a sphere, you have a sphere sitting at every point on U. And similarly, if you work with advanced coordinates, then you get what is known as past null infinity. So these two are really the boundaries of Minkowski spacetimes, and they don't really talk to each other. And this is a point which will be important for us. So they are both topologically disconnected cylinders. I mean, if you are a relativist, then what you would do is you'll add a point at spatial infinity, which would basically crunch these two cylinders and sort of join them together. But so if you go to large distances, sometimes you will see that there is a notion which is called I naught, which is really not a sphere. It is just a point, and that's a point where both these cylinders crunch and sort of sit together. But that's not a very useful notion to do physics, I think, because everything becomes singular there, because it's just a point. So it's something that we will avoid. Although there's something we will have to do later in the talk at spatial infinity. So right now, these are our boundaries, two disconnected sort of null infinities. And now the idea is that suppose we look at classical equations of motion for the theory in sort of off null infinity, in the way we do in ADS in kind of Pfefferman-Graham gauge. So then they show sort of interesting behavior. So let's try to look at the equations. And of course, we have the Bianchi. And what we want to do is sort of expand field in 1 by R expansion of null infinity and see how these equations behave. There's one thing I will do though, because I'm sort of interested in looking at soft theorems with definite helicity. So here I looked at soft photon, which has negative helicity. So I will work with, instead of working with this sort of real Maxwell's equation, I will work with self-dual equations. You will see why they are more useful, because self-duality and helicity are directly related. So let me define self-dual FAB, which is just, as you all know, which is just, and they satisfy, there is no Bianchi for them, but they satisfy the same equations, and of course the self-duality constraint, which is. And now usually when these are the sort of classical theory problems that people have studied, Penrose especially has studied long back. And the idea is that you have to give certain fall-off conditions, exactly as in ADS on these fields, to solve the equations. And the standard fall-off conditions, which ensure that you have non-zero but finite radiation, which leaks out at infinity, are as follows. So I will just write down the fall-off conditions because we will kind of use them later. So as I said, we are doing a large R expansion, keeping U and X hat fixed. And so this is the expansion of FUR. And the leading term really, this is like electric field, so we expect it to fall off as 1 by R squared. And then the other data, for example, if you look at, sorry, I should have said one thing. Let me coordinatize the sphere, this is S2, with stereographic coordinates, Z and Z bar. Then the other sort of other fields, for example, if I look at, say, AZ bar, function of UR and X hat, its fall-off condition, fall-off behavior, sorry, is given by, there is a zero mode, which doesn't fall off, and then there is a order 1 by R behavior. And of course, similarly for the currents, you will have some fall-off behavior to ensure that the total, yes.
Yeah, shouldn't the radiative electric field fall as 1 by R? Or?
Yeah, that will come from here.
Okay.
Look at the radiation, that will come from this component from here.
So this F plus that you're writing down doesn't have the radiation part, it's just the Coulomb part or something.
Right, but they are of course all intertwined. When you solve equations because of Bianchi or self-duality constraint, they are not independent of each other. So since you are asking, let me say that the whole idea here is that you give some free data at null infinity, and then you can solve order in 1 by R for all the other components of the gauge field. And the free data is going to be AZ and AZ bar, and certain free data for the scalar. So this is free data. 1/2 of free data. There's similar one for AZ. And once you have that data, once you have this, and similarly AZ, you can solve Maxwell's equation order in 1 by R for all the other components. And then similarly, there is going to be a follow-up behavior for these currents. So for example, let me write down some of them. So J, let me just write this as J. So J R will go as 1 by R to the 4. And similarly for JU. And then the whole idea is that the free data is really given by this AZ and AZ bar and the sort of the scalar field leading behavior of scalar at the null infinity, and you can solve everything else in terms of this free data, which is like in ADS in Pfefferman-Graham gauge. Okay, so now let me just write these equations, of course will be complicated, but let me just write two equations which will be relevant for us. So you can look at the following equation, which is the leading order equation for FUR, which is what Luga was asking. So if you look at the leading order equation for FUR, which I called FUR0, which is a component that fall off as 1 by R square, then that goes as JU minus notice that there is no Z here because I'm looking at, I suppress here, but I'm looking at the self-dual component. So it kind of distinguishes between Z and Z bar. So now, okay, so now this is what Schrödinger showed. What he showed is that if you take Weinberg's theorem, then that is equivalent to looking at the following word identity. Where this Q epsilon, sorry, maybe I will write it slightly differently. Q epsilon, so Q plus epsilon, for example, is a charge or rather flux which is defined at null infinity, and it is given by you integrate over the entire future null infinity, and you have whereas epsilon is just any arbitrary function on the sphere. So these are really infinitely many word identities, because for each epsilon you have a word identity. And what, if I get time later, I will sort of show how he derived it. I will sketch the proof. But the idea was that this is the same statement as Weinberg's photon theorem. So the statement is that if these charges are conserved, that is if Q plus epsilon is equal to Q minus epsilon, then that is same as Weinberg's photon theorem. And this is really equivalence. I mean, you can go from one side to the other. But actually, even though this charge looks like it is it's like a flux at null infinity, it has a slightly more sort of nicer behavior, which will be very important for us using this equation. So if you see, this quantity which is appearing here is really the total U derivative. Just so then when we substitute that, we can easily see that our Q plus epsilon is given by integral over the sphere minus, of course, the zero component, the zero coefficient. And if you assume that, which is what is usually assumed, is that nothing leaks out far in the future, that is nothing goes, nothing leaks out here, then this F plus UR at U equal to plus infinity is 0. And then your conservation statement becomes very, kind of transparent. I will erase this. And the conservation statement is that integral at S2, F plus UR at U equal to minus infinity, x hat epsilon x hat equal to at V equal to plus infinity x hat epsilon x hat. But this is, soft theorem tells us that we require this for all epsilons. So basically what that is telling you is that these conservation laws are tantamount to saying that if you look at F plus UR, zero component at u equal to minus infinity, then they should match plus VR component at v equal to plus. So in some sense, the problem reduces to looking at analyzing the physics here on this sphere, on this sphere for these charges. We are saying that the fact that Weinberg's soft theorem is true is simply because these two things are equal. So now let's try to see, so this is for the leading soft theorem. Let's try to see what is the analogous statement for the, so is there any question so far? Yeah.
At tree level, right?
So far we are not at tree level yet.
This is exact.
This is exact, yes.
So the x hat dependence, how does it translate to in the soft theorem? I mean.
Oh, thank you. Yes, because the soft factor. Yeah, I was planning to sketch it later when I do the more general proofs. But the basic idea is that if you look at soft factor, it is as we saw, it is given by epsilon mu pi mu divided by pi dot q. And we are looking at massless scalars. So each of these p is also null. So each of these p is really coordinatized by its energy and its direction, which I can think of it as something on the celestial sphere. So if you take a particle, massless particle with a momentum p and you shoot it, that at null infinity, it will hit the point on the sphere, which is precisely its direction in the momentum space. So because of the stationary phase approximation, it localizes. So that's what translates the p hat really into x hat in the. Okay, so now we would like to say that, see, what is a similar conservation law for the next theorem, which is the subleading soft photon theorem or Lowe's theorem. Oh, sorry, shouldn't have. So here, what people found was a little bit surprising, again starting from the Harvard group and many other people, is that the statement that one has the, so let me rewrite the statement of Lowe's theorem. And the statement said that if you look at the following soft limits, you take, I will write out, by out I mean all I will not write P1 to Pn from now on, it's just the out state of the theory. This is S. So I did not write it before like this because I was expanding in omega. But if you want to extract out just the order omega to the zero term, then you just do this operation, and only this term gets isolated. And now what people showed is that this statement is equivalent to the following word identity. Where this q plus y, in contrast to the charges here which were parameterized by the function on the sphere, are charges which are parameterized by actually vector fields on the sphere. I mean, the detail actually form is not important, just for completeness, I will write it. Sorry, maybe I shouldn't start it, but anyway, I will just write it. So we get plus anyway, the form is not important. I just wanted to say that it depends on the vector field like this. And my plan was to sort of sketch the proof of how we get here from here to here later, because when I do the general proof, but so for now, please believe me, unless you have a question, is that these two statements are equivalent if you think of these charges given by these kind of fluxes here. But this charge doesn't quite look like I mean, here the statement was very nice. We could sort of say that something was equal to something at the spheres which were sitting at boundaries of null infinity. So let us try to see if this kind of nasty looking object, we can do something better.
whether this expression is related to F1 or something like.
Oh, thank you. Yeah, I mean not quite F. Yeah, yes, exactly. Actually, exactly related to F1. So yeah, maybe let me do that. So there is, in order to sort of write this in a more manageable form, I'm going to write. I wrote one Maxwell equation so far. It was like the leading order in our Maxwell equation. But of course, if you go to higher order in R, you get a hierarchy of equations, and they sort of look not that, in some sense, not that bad. So if you go to like R to the nth order, or R to the n plus 1th order, let me take that convention, then this thing satisfies the following equation. I mean, this is again just playing with Maxwell equation, and we can get this equation. Where this box is the Laplacian on the sphere, on the celestial sphere. Because remember, all these FURs are function of only U and X hat. There's no R dependence in them. And this Sn is some complicated functions of JUs and GRs. Some movements of JUs and GRs. So that's not very important for us. There's some equation like this. And using this equation, what you can show is that this charge can be written as follows. Which is exactly what Rajesh was asking. So this charge is equal to this charge if the vector field y is related to this function epsilon just by gradient relations. So this is just a consequence of Maxwell's equation. So the idea is that this charge, which looked a bit mysterious in the sense it was parameterized by vector field as opposed to large gauge parameter, and has a kind of a complicated form, can be just written in this form. Again, as a total derivative in U. And now it turns out that, so again, if you assume that nothing leaks out at in the future, then this basically tells us that there's a similar conservation law to the one we have here, which is given by at u equal to minus infinity is equal to at x hat is equal to exactly the same relation at v equal to plus infinity. Okay, so it is nicer than than what we had before, but still there is, I mean, one can make it better, and that would be like really key for us. So is there any question till this point? So again, we see that really these infinity charges are a consequence of certain equalities of these fields that these spheres, and the fact vector field was appearing here was not I mean, it was in some sense an incorrect description. Really, this vector field is nothing but, I mean, there really is always a large U1 gauge formation which doesn't die down at infinity, and it is that which parameterizes all these charges. But now actually there is more we can say about this quantity, because so far we have only done an expansion in R, but we can also do an expansion in U, because we are really interested in studying physics in the neighborhood of large U, so we can sort of do an expansion in 1 by U, and that tells us more about what this quantity is. So let me just do that. And that will set the stage for how to understand all the other theorems, the other soft theorems. Yeah.
So you said that, for example, if there are, if the 3-point function of the photons is changed,
Yeah.
then this second result will change.
That's an excellent question. Actually, it is not this result that changes, but it is when you write this in terms of the currents.
Okay.
Yeah, because the currents change.
Mm-hmm. So in this statement is that the part of the electric field that you're looking at to get this soft theorem is it's the same, yeah. But how the currents produce that part, that depends on the theory.
Yeah, that depends on the theory, right? So if you just we want to understand what is the large U behavior of all these fields. And let me just write something and try to justify it. So if you look at, for example, the nth component, which is the 1 by r to the n, or 1 by r to the 2 plus n power of FUR as a function of u and x hat, then this admits an expansion in 1 by u, and then expansion is given by and this, you can immediately convince yourself that this is true by just sort of meditating over this equation. Because it is telling you that if you started with FUR0, which had a certain fall off in U, then FUR1 will have one higher power in U, because rho U of FUR1 is sort of FUR0. So it will immediately tell you that this is true. There's a small technical caveat that I will just say, that this solution, this expansion in large U is true if and only if the matter fields have compact support in U. Which is quite a reasonable assumption. I mean, in the sense that we don't want, we are not looking at soft particle for the matter. So matter can be localized somewhere and getting scattered, etc. But in order to go from this equation to here, this is a sort of a technical thing that is needed. Anyway, once you have this, you can immediately see that if you look at FUR1, then it is an expansion which is U FUR 10 x hat, some particular movement of FUR plus FUR 1 x hat plus order 1 by U terms. And again, using equation of motion, you can show that this particular combination, I shouldn't cross here. Maybe I'll write it here. This particular combination that we have is nothing but FUR 1. So let me just call it, since I keep using it, let me call it star. So again, using star, we can show that this particular combination, which is FUR1 minus 0 at U equal to minus infinity, x hat is FUR 1 x hat. Which means that these conservation laws, which gave rise to Lowe's theorem, kind of reduced to a very simple relationship between the fields at the boundaries of null infinity. So we are now saying that Lowe's theorem is equivalent to FUR 1 at x hat is equal to FUR. So now this kind of set the stage for how it would go. Once we have understood this, now it kind of set the stage for how the higher order relationship would go, right? In the sense that now let me make a claim that, which is what I will, now there are two questions. One is sort of, why is this true in classical theory? I mean, we should be able to prove this in classical theory if this is indeed true. So that is one question. Why are these asymptotic symmetries or conservation laws true classically?
So the equivalence doesn't depend on being at tree level, but the truth of the two sides depends on being on tree level. Is that?
Right. I mean, because this is a classical statement. Right now, this is a classical relationship, and this will unambiguously go to word identity for the tree level amplitudes. But if your S matrix itself has an efficient divergence, then there will be subtleties.
Oh, so the failure, including loops, is due to IR divergences?
IR divergences, yes.
Is there some other form where you deal with the IR divergences and you have something that's true?
Yeah, that's I wanted to say something about that in the end, but the idea is that in 4 dimensions, this expansion itself breaks down in the sense that the Lowe's theorem is order omega to the 0 term. But if you include IR divergences, then you get a factorization at log omega. Now this factorization of log omega is also universal. in fact, it's in some sense more universal than this theorem because it doesn't even depend on these higher point functions of the theory. But how to understand that in terms of asymptotic symmetries is not clear. But I would maybe mention it in the end, briefly. Okay, so this is one, and the second is how does one generalize this? For other, for the remaining soft theorems, for Sn soft theorems, where n is greater than 0. Okay, so these are the kind of the two statements we want to sort of understand. I mean, the two questions whose answer we want to find out. And so for the second question, let me first make a claim, and then I'll try to sketch a proof. So the idea is that if you look at following charges, so suppose I want to prove the sort of essence of theorem. Okay, first of all, there is an immediate, you will say that this cannot possibly be true, because if I have a word identity parameterized by say some, let me call it T, then you would expect it to give you a factorization. But we know that all the theorems after the subleadings of theorem are not factorized form. So they have one term which factorizes. Let me write it down. So remember that the theorems where, if I look at say, So let me write down this Sn soft theorem again. So this is the way you isolate one term in the soft expansion. You get some operator S hat n, which acts on Mn, plus you got a remainder which was not even factorizing, which we call Rn. So it looks like, immediately it looks like that this won't be true, that how can this thing which is not factorizable can be written in terms of a word identity, which will typically give rise to some factorization theorem. But the idea is that this Rn has a particular structure. So see, the Rn actually has a very peculiar structure, a very specific structure, which is given by, it is given in terms of some tensor, which is a function of, suppose you are looking at Sn theorem, so it is n plus 1th rank tensor, which is a function of this momenta, times you have epsilon mu, q mu1, q mu1. And this tensor has a specific, for any, it has a specific property that it's antisymmetric in any mu and mu I. So between any mu and mu I, it's antisymmetric. So if you can somehow project out sort of only the symmetric part of this combination, then this non-factorized term will drop out. Does it make sense? So there is a way to take a projection out of this theorem, so that one only gets this information about the factorized part, which is, I will show it. Yeah. So I'm saying that suppose you take this quantity and you do the following operation. You do dou by dou q mu1 dot dou by dou q mu1, and then you tensor it with some index, some tensor which is omega mu1, which is completely symmetric. If you do that, then it will kill this part because of the antisymmetry of mu near the mu I. So if you sort of multiply, if you operate on both sides of this theorem with this kind of tensor, then this term will drop out and only this one will remain. So it has very partial information of the full theorem, because really all the dynamics is in some sense contained here, but you get a factorized form. And that is what we will obtain from these conservation laws. So let me make a claim and proceed. So the idea is that if you look at following charges, let me parameterize them with T, which are given by, epsilon, because I always use epsilon, which are given by, again, integral over scri. then it is precisely these charges whose Ward identity give you this factorized term in the soft N theorem. That's the claim. So, all the higher order soft theorem come from the conservation laws, which are given by, if you look at FUR NN, X hat is equal to FVR. So the statement is that if classically we could prove that this is true for any n, then we now understand that how do we get these soft theorems for tree level scattering amplitudes. So this is the hierarchy of, like infinite hierarchy of infinitely many conservation laws. And this can be generalized to gravity. I'm just giving a simple example, scalar QED case. So there are two things I have to do. I have sort of running out of time. So there are two things I have to do. First, to sort of prove this claim and try to sketch why is this true classically. So maybe the classical thing is a little more interesting. So let me do that because the other thing is more of a computation. So I will try to argue why these kind of statements are true, at least classically. It looks a bit complicated because these things are defined on these two spheres, which are not talking to each other at all. So we have to somehow make a sort of do something so that they start talking to each other. But for that, we have to focus on spatial infinity, which we haven't done.
Can you say more about this projection? I'm quite.
Oh, okay.
I mean, what is the physics of it and what is happening?
No, I mean, the idea is that there is a way to isolate this term. That's all I'm saying. I mean, because of the particular tensor structure contained here, there is a way to isolate this term, and that is sort of that's a factorization theorem. But it has very little dynamical information because it has completely lost information about this Rn. But that is what you get from Ward identity. That's all you get from Ward identity. So when I do the maybe if I get time, if I had done the other one to prove. If I start with this and put it in matrix element, in the S matrix, and do a computation, you will see what I get, which would sort of not have this piece and have this piece. Because of operations like this. Maybe I'm not saying it properly. Let me do the classical thing and then, yeah.
Then all these are, so there's a Bose symmetrization of the amplitude, right?
Yes, yes.
So this derivative that you're writing down, it seems to me that it will just automatically be symmetric or? Well,
I mean, these are derivatives of soft momentum. This Q is a soft momentum.
Soft momentum. Okay, so you're deriving with respect to what to what?
So this is dou by dou Q1, dou by dou Qn. So this is, remember, this is n soft. So each term has n soft powers of soft momentum. So when I differentiate this, I will get something which includes, I mean, it will differentiate these Qs. But I'm projecting it, I'm contracting with a tensor, which is purely symmetric. So this is anti-symmetric.
So you have n soft photons?
Yeah. No, you don't have n soft photon. You have one soft photon, but it's your power of Q is nth, right? Okay. Omega to the nth power.
Mm-hmm. So now why is this not, the statement is not completely symmetric in Q? I would think if you just expand in Q.
Yeah. It's completely symmetric in Q, but of course the A has extra index mu, which contracts with the epsilon. And it's anti-symmetric in mu and any other mu I, which is a statement really of gauge invariance, because if I put epsilon mu as Q mu, it will trivially vanish this term. It's that anti-symmetry that help projecting out this term. Okay, so let me try to sketch why these kind of things are true classically. But in order to do that, we have to make some make these two spheres talk to each other. And there is a way to do it, which is to understand better the structure of spatial infinity. Now, as I was telling you, that usual sort of Penrose and old school definition of spatial infinity is it's just a point, which is sort of more traditionally called I0. But there's a better way to understand the spatial infinity, and that is by working with hyperbolic coordinates. So what we want to do, let me first tell you pictorially what we will do. We'll blow up this I0. So we will sort of cover it with a three-dimensional de Sitter space, such that the boundaries of the de Sitter space match with these two spheres that we are talking about. And then what we'll do is study Maxwell's equation on this de Sitter space and see why these kind of statements are true, just by studying propagation of fields on this de Sitter space. That's the basic idea of the proof. And the whole thing becomes very simple, because if your matter has compact support, then the Maxwell's equation in the vicinity of this de Sitter space are just pure vacuum Maxwell's equation. So it's like just free fields propagating. And proving this is just playing around with some Green's function and doing some asymptotics. But that's the basic idea. So it's to sort of zoom in on the spatial infinity and make these two spheres talk to each other. So this, so there is a way to blow up I naught. Which is to work with the following coordinates. So you take a sort of hyperbolic coordinates, take a coordinate rho, which is in tau, which is by rho, and then your space-time metric. And so we want to study a large rho limit, because if rho is large means R is large. So if you keep T fixed and take R large, then rho becomes large. And then this is given by d rho square plus, I may be forgetting the, so this is a three-dimensional Lorentzian de Sitter space. So that's what I naught looks like in these coordinates. It really is that. And one can easily check that if you take tau goes to infinity and keep the sphere direction fixed. So it is coordinatized by, this boundary is coordinatized by tau, which is a time coordinate, and the sphere. And you can check that global de Sitter, yes.
Okay. And eventually you will take this time to 0, or?
No. We'll just keep it like that. And the idea is that if you take this de Sitter and you take tau going to infinity limit, this matches with the u equal to minus infinity sphere. It smoothly patches up without any singularity. And similarly the past one. So now what we want to do is to study Maxwell's equation in the vicinity of this de Sitter, or rather at spatial infinity, and prove this statement for any n. That's what we want to do. Let me try to sketch the basic idea.
Can I ask a question? So, is this the conformal boundary just with respect to a different choice of conformal factor?
Yes, exactly.
Which is the same as you approach scri plus and scri minus, or I plus and I minus, but is different when you approach I naught, or from the standard one?
Yeah, it is certainly different. I don't remember if it is the same one as when you approach scri plus. It is also certainly not the same one when you approach I plus, because I plus is also a point. But what you can do is, you can similarly, exactly like this, you can blow up I plus also, with coordinates which are sort of Wick-rooted version of these coordinates, so that I plus will be covered by some space-like hyperboloids, which is Euclidean anti-de Sitter space. And there also the conformal factor will be different than the one usually used to approach I plus. But yes, you are right that there is a different choice of conformal factor which ensures it does this.
So all the vacuum, no cosmological constant Einstein equations?
I mean, this is a boundary of the, so you're just adding boundary like how you usually do, just as he's saying, right, that you use a different choice of conformal factor to add the boundary. So the full metric is of course conformally related to the physical metric, which is solution to Einstein's equations. Okay. So, but essential idea, I hope I've already conveyed that the fact that, remember we had a technical caveat which I had introduced, which is that matter have compact support at scri. So what this means is that the Maxwell's equation becomes sort of source-free equations at spatial infinity. And they look as follows. So if you, again, people have studied in this new conformal compactification, what is the asymptotics of Maxwell fields? And let me just write down some fall-offs. So for example, if you look at alpha rho fields, which are where alpha is any coordinate tau or x hat, then its expansion is given by 1 over rho. Again, I think this was studied by Garrosh and Newman. And similarly, if you take f alpha beta, for example, then it really goes as. And the equations that they sort of satisfy are and Bianchi or self-dual constraint, depending on what you are working with. Let's say Bianchi. They are source-free equations. And now, what you want to do is, there are two things you want to do. First, you want to understand what is the relationship between FURRNN and this F alpha rho or F alpha beta fields. That is the first thing you want to do. And then, once you do that, you want to study propagation of these fields and prove that these conservation laws are. So first thing you want to do is, I have 2 minutes. First thing I want to do is find relationship between F alpha rho, F alpha beta fields and FUR. NN. And this is actually not very difficult to do because of the fact that since we know what is the fall-off condition, so we know how we got this by looking at a large U behavior of the F fields. So, okay, this is some, I will not do the algebra, but since we know the large U behavior of this F field, we can go from UR coordinates to rho tau coordinates. And what you can see is that the large tau behavior of these fields, which is consistent with the large U behavior of this field, is given as follows. So if you look at F rho tau, say of power n, and you start expanding it, this is a function of tau and x hat. And if you start, I want to study large tau behavior of this quantity. So I want to study 1 by tau expansion of this quantity. And what you can show is that this is given by, which is consistent with the U fall-off, is given by 1 over tau to the n plus 3, F rho tau, let me call it n0, x hat, plus lower order terms. And it turns out that this F rho tau n0 is exactly equal to FUR NN. Okay, so that is the first step that we have to do. So now we have basically been able to, so now what we want to show is that if you take F rho tau n0 x hat, and if you evolve it back, or if I had started with FVR, you evolve it in front, and you go all the way to tau equal to minus infinity, then you should get back FVR NN. But since these are free field equations, what you have to do is just take some retarded Green's function and evolve it and do some asymptotics. And then you can actually show that it is indeed true that these two things are equal. So that kind of proves that simply because of the whole thing is very, very simple because it's a source-free Maxwell equation. And so that proves classically that proves the equality of these two things. So at least it tells you classically why all this infinitely hierarchy of asymptotic charges are conserved in these theories. Okay, I couldn't finish the proof. I wanted to prove how these SWOT identities give you the soft theorems, but I ran out of time, so maybe I just stop here and take questions.
So last time there was a condition called Christodoulou-Kleinerman condition.
Yes.
What does that do here, or is that relevant?
Yeah, no, that's very relevant. So that condition is the first, when we proved that, I mean, that was in gravity, but I'm giving you the analogy in here. If you take FUR 0, 0, which is equal to FVR 0, 0, that's the Christodoulou-Kleinerman.
Yeah, so you had this polynomial part R at some point, which had this specific symmetry property that was killed by symmetrizing all the indices.
Yeah.
Can you explain again why it cancels in this relation between field strength approaching from the past and future?
We are seeing how from here we get that.
Yeah, although I see that this R does not contribute to that relation.
Yeah, R doesn't contribute to that relation. So you are asking why? Is that
Yeah.
So that is because of the following. Okay, maybe I will just sketch the. Can I take 2 minutes? So maybe I will just sketch the proof that I think that will.
Or we can do it later, maybe in private.
Yeah, I can do it.
Okay, good.
Yeah. So let me first tell you how we go from the. I mean, this will help actually. Let me tell you how to go from Lowe's theorem, which did not have R actually, but it will help us sort of set the stage to the word identity for FUR11. And so the Lowe's theorem really looked like, I mean, we could rewrite it as 1 to 0. Is equal to some differential operator, which I will suppress all the symbols. And now the way to go from here to the word identity is the following. You smear both sides, I mean, both sides of this quantity, you do the following. You integrate both sides with where y is any arbitrary vector field. So if you do that, then what happens in this side is you get S1, and this dz square S1 gives you some combination of delta functions in the sense that it will give you like something like this.
Only to the part which give you delta functions on the
Exactly. Now, no, but yeah, right. And now what happens is that if I want to generalize this to say n theorem, then I have to do the same thing with, so for S0, I am differentiating with 2 derivatives.
Yeah. So this so-called polynomial part of the amplitude does not have any delta functions, so it never contributes to that.
If I take dz to the n+1 and apply it on the, because this is acting on the q's, and it's an n degree polynomial in Q, this is an n+1 differential operator, so it just kills it.
Okay. If there are no further questions, let's thank Alok again. We break for lunch and meet at 3.